We're continuing chapter 19 here, the kinetics of radioactive decay. So, radioactivity is natural. And I think that's something that's not necessarily obvious to everybody. All elements that have more than 83 protons, and some that are smaller than that, are unstable and will give off radioactive particles or energy.
183 or 83 and more? Ooh. 83.
Over 83. Bismuth is stable. Yeah.
So starting with the parentheses.
Now, bismuth could have some radioactive isotopes, but all the elements larger than bismuth are always radioactive and unstable. They don't have any stable isotopes. So, we have this, in our culture, we have this idea that natural things are good and natural things are safe. No. Gamma rays are natural. Are they good for you? No, they're not. So just because something is natural does not mean that it's good, safe, beneficial. So why are there radioactive nuclides, radioactive atoms still around? Because they're decaying all the time. They're still around because new ones are being created constantly. And so the existing ones decay, new ones are created. Some of the ones that are decaying decay incredibly slowly. So they're just going to be around pretty much forever. So all that said, radioactive decay is via first order kinetics. So this is touching back on that first chapter, chapter 13, first order kinetics. So in first order kinetics, if you remember, hopefully, the rate of the reaction is proportional to the number of nuclei, to the concentration of reactant. So the rate is equal to some constant times the number of radioactive nuclei. Some of these radioactive substances have large rate constants, some have small rate constants. So it's all over the place. We talked about half-life when we talked about chemical kinetics. That applies to radioactive decay as well. The half-life is the time it takes for 1/2 of the parent nuclide in a sample to decay to the daughter nuclides. And so this is the same equation we saw for first-order chemical reactions. T1/2 is 0.693 divided by the rate constant. So if you have a nuclide that decays quickly, it's going to have a short half-life. That means it's going to have a large rate constant. Such nuclides are considered to be very active, and in terms of thinking about the decay, there are many decay events per unit of time. Other nuclides decay very slowly. Thorium-232 has a half-life of 14 billion years. That's a long, long time, right? Older than the universe, most likely. So if you started with 1 million thorium atoms, which in terms of numbers of atoms, is that very many atoms? No, it isn't. Because 1 mole is 6 times 10 to the 23rd atoms, right? That's way more than 1 million. So it's going to be a small amount of substance. But after 14 billion years, you still have 500,000 of them left. And another 14 billion years, now you have 250,000 left. What's very important to remember is that the radioactive sample does not decay to 0 in 2 half-lives. I lost my words. That's a conclusion that has no basis in fact. You say, well, if it took 5 years for half of it to decay, then in another 5 years the rest of it will decay. No, because it's proportional to the number of atoms that you have. So the rate gets slower and slower as it decays. So every half-life, you cut your sample in half. Radon-220 has a half-life of 1 minute. Very short half-life. So if you start with 1 million radon-220 atoms, after 1 minute, you have 500,000. After another minute, you have 250,000. it'll decay down to 1,000 atoms in 10 minutes. So that stuff disappears pretty quickly. We can look at graphs like this, comparing atoms of radon to over time, and we see that it goes from 1 million to 500,000 in 1 minute. Every minute, it gets cut in half. So the difference gets smaller and smaller as you go along. And just sort of for interest, there's a table of some nuclides and their half-lives. And it also gives the type of decay that they undergo. So these are ones that might be interesting. Radon is interesting because in some parts of the country, radon seeps out of the ground. And so if you have a basement, you can get radon in your basement. So radon is an alpha emitter. What did we learn about alpha particles in terms of penetrating and ionizing? High ionizing power, low penetrating power. But is radon a gas, a liquid, or a solid at room temperature? It's a gas. So it comes out as a gas in your basement. You go down into the basement to wash your clothes and you breathe it in. Is that dangerous?
Yes.
Really, really dangerous. So, you know, I spent part of my life in Iowa where there is natural radon gas in the soil. And so people have radon detectors and there's radon abatement companies that'll seal off your basement and all kinds of stuff like that. It's got a very short half-life, but it just keeps coming in from the ground. So that's kind of a bummer. Yes?
You said radon. Is that number 88?
Radon is 86.
86.
Noble gas.
Radium.
Radium. Radium is also radioactive, but it's a solid at room temperature.
I just noticed that it happened to be considered stable. Is that correct?
That's a good question. It's bigger than 83, though. I'm not sure. You know, it could be that its half-life is long enough that they can get a decent reading on it.
At that half-life, I understand why it's
No, that's not stable. Radon is definitely not stable, and that's why the atomic mass of radon on the periodic tables in parentheses is 222. That's based on the different types, the different isotopes of radon. Radon 220 obviously would have an atomic mass of 220, pretty close. But you can't weigh this stuff because it's, you know, in a minute half of it's gone. It's not really gone, it's turned into something else, but it's still a problem in terms of determining an atomic mass. Any other questions? The integrated rate law, we derived this back in chapter 13. And this is what we used for chemical reactions that were first order. We get a relationship between the concentrations of the reactant and time. Because the rate of the reaction changes over time. And so the natural log of the concentration of reactant A at a particular time is equal to, I'm sorry, I was distracted by the potato chips. Start over. The natural log of the concentration at a particular time divided by the initial concentration is equal to negative KT, where T is the time we're interested in, and K is the rate constant. You know, they'll probably be able to hear that on the YouTube video. No, I want the whole bag is what I want. So for radioactive decay, we can just substitute the number of nuclei instead of talking about a concentration. So the natural log of the ratio radioactive nuclei at time t divided by the initial amount is equal to negative KT. So we can do problems like this. Plutonium-236 is an alpha emitter with a half-life of 2.86 years. How long will it take for a 1.35 milligram sample of plutonium-236 to decay to 0.100 milligrams? Now, in lower chemistry classes, we do something like this just by cutting things in half. But we're in the big boy class now. And so we actually use the mathematical equations. So there's a couple of equations that we just talked about. What color? Dark blue maybe. Seems like a dark blue day. T1 half, remember what that equaled? 0.693 divided by K. So since we know the half-life, 2.86 years, could we figure out what the rate constant for this decay is? We sure could. We'll take K is equal to 0.693 divided by the half-life. Oh, I didn't do it for that one, because that would be too simple. So 0.693 divided by 2.86. So this gives us a rate constant of 0.242. I'm going to keep a couple extra digits. What are the units on that rate constant? Per year, or year to the minus 1. You got to keep track of your units, because when you find T, you want to know, is that seconds, hours, years, millennia, what is it? So we calculated K, and then the other equation that we looked at was the natural log of n at time t divided by n initial, and that was equal to minus kt. So we are trying to find the time. 1.35 milligrams is the initial amount. Now, is that the number? Oops, not T, 0. Is that the number of nuclei?
No.
No. What would we have to do to get the number of nuclei? Yeah, we'd have to use Avogadro's number and the molar mass, right? But this sample, this number is also in milligrams, and it's milligrams of the same thing. And since we're looking at a ratio, those things would cancel out, wouldn't they? So we can use masses in place of the numbers of nuclei, provided that it's masses of the same thing. So that's N0, and then this is NT. I should probably not say equals. It's proportional to, right? There we go. Let's be precise. So then the time is going to equal minus 1 over k natural log of nt. I don't know why I dotted my t. And we're not going crazy about significant figures here. We just need to use some common sense. I really don't believe it's ever a good idea to round off intermediate values. So this has 3 sig figs, our half-life has 3 sig figs, and so this rate constant has 3 sig figs. But let's carry a couple extras to avoid rounding errors. NT is 0.1, and N0 is 1.35 milligrams. Those units are going to cancel out. I'm going to write the answer up here. It's like a train going down the hallway. So I came up with 10.7 years. Does that seem like a reasonable number?
Oh, yeah.
Half-life is 2.86 years. Cutting this in half would be like 0.65 or so. and then you cut it again. You're going to cut it in half several times before you get to 0.1. So 10.7 is a reasonable number. If you come up with a, like the first time I mispunched a button, I missed a decimal point, and so it came up with 0.107 years. And I'm like, now wait a minute. That doesn't make any sense. So that's when you do the calculation again, and you're like, okay, that's better. Then do it again, because you go for best 2 out of 3 when you do something like that. Any questions?
So the decay was something per year, and the T is years.
Right, because this is 1 over years, which equals years. So pretty much whatever unit you have on your rate constant for time is the unit that's going to end up on your time, and vice versa. If they tell you it took so many minutes to do this and they're asking you for the rate constant, if you don't convert any time units, you'll end up with a rate constant per minute. Oops. So mass is directly proportional to number of nuclei. And because there's a ratio in here, we can use initial and final masses instead of initial and final numbers of nuclei. That's what we did in that problem. Rate of decay is also directly proportional to number of nuclei and can also be used. So this is 2 different versions of the integrated rate law. The natural log, those are upside down, aren't they? One of them's upside down. No, they're both upside down. Stop it. There, I fixed it. It's the rate at time t divided by the initial rate, or the mass at time t divided by the initial mass. The natural log of that ratio is equal to negative kT. We can utilize these rates of reactions and half-lives for radiometric dating. As I'm making up these slides, it's like radiometric dating is like, is that like speed dating? Or, it sounds like some type of dating. So I'm sorry if I giggle while I'm explaining this. I just can't get that out of my head. At least it never says radioactive dating, because that, I don't know, glow in the dark, you don't even need candles. Radiometric dating is using the predictable decay of radioactive isotopes to estimate the age of rocks or other artifacts that have those isotopes in them. And we're going to talk about 2 types of radiometric dating. The first is radiocarbon dating. This was devised in 1949 by William Libby at the University of Chicago, and it makes use of a radioactive signature that results from the presence of carbon-14 in the environment. And he received the Nobel Prize in 1960 for this work. So, how does this work? Carbon-14 is constantly formed in the upper atmosphere. It's radioactive, and in the upper atmosphere we've got nitrogen, because nitrogen is the main component of air. Nitrogen is getting bombarded by neutrons, and that causes this reaction. It causes the generation of carbon-14 and a hydrogen atom. Well, that carbon-14 is radioactive and decays back to nitrogen through beta emission. The half-life is 5,730 years. So that takes a while to happen. So there is carbon-14 continuously being formed in the upper atmosphere, and then it's continuously decaying. And so the equilibrium amount of atmospheric carbon-14 is fairly constant. Not absolutely, but fairly constant. So there's radioactive carbon atoms in the atmosphere, and those get oxidized into carbon dioxide. There's lots, there's not lots, but there's carbon dioxide in the air. And what happens to carbon dioxide? Plants use it. Plants use it in photosynthesis to create sugars and starches and cellulose and things. So it gets incorporated into the plants. Animals eat the plants. It works its way up through the food chain. So pretty much everything that is alive contains the same ratio of carbon-14 to carbon-12 as that found in the atmosphere. So, did you know you had carbon-14 in your body? You have radioactive isotopes in your body. But it's okay. It's always been that way. It's fine. It's a very low level. What happens when something dies? It stops taking in carbon. The carbon-14 that was in that organism at its death stays, but no new carbon-14 comes in. That carbon-14 decays with a half-life of 5,730 years to nitrogen. And so we can measure the ratio of carbon-14 to carbon-12, and based on the half-life, we can estimate how long ago that organism died. We do not use this like in crime scenes, you know, did he die at 3 o'clock or at 2 o'clock? It's not going to help us with that. But it does help us with thousands of years. The maximum age that you can really use this for is up to about 50,000 years. The reason we can't go back any farther is because after 50,000 years, the amount of carbon-14 in the organism is so low that you can't accurately measure it. So that becomes a problem. We can check the accuracy of this technique by measuring the age with radiocarbon dating of objects whose ages are known from historical sources. And in doing so, they find that there's a deviation of up to about 50, I'm sorry, that's not a 15, that's a 5, up to 5%. And they think the reason for that is due to variations in the atmospheric carbon-14 levels over time. It's nearly constant, but it isn't absolutely constant. So if the carbon-14 levels were a little higher or a little lower when that organism was alive, that's going to affect the ratio that we see thousands of years later. One cool way that they correct for this is by looking at western bristlecone pine trees. These things can live for thousands of years. And if you know anything about trees, as a tree grows, the trunk of it grows in rings, right? And every year a new ring of wood forms. The wood that forms in that ring incorporates carbon dioxide from the atmosphere. And so you can study the individual rings of a bristlecone pine tree and learn about variations in the carbon-14 content of the atmosphere during those years. And because these plants are still alive, you can figure out what year you're looking at. So it's pretty neat. So here's an example problem. A researcher claims that an ancient scroll originated from Greek scholars in about 500 BC. A measure of its carbon-14 decay gives a value that is 89% of that found in living organisms. How old is the scroll, and could it be authentic? There just doesn't seem to be a lot of numbers in that problem, does there? Well, carbon-14, radiometric dating, we need the T1/2. So T1/2 for carbon-14 is 5,730 years. Where is the information hiding about the ratio? The 89%. So 89%, the carbon-14 level currently is 89% of what it was originally. 89% is a ratio of 89 to 100, or 0.89 to 1. That's equal to the ratio of the carbon-14 at time t, which is now, divided by the original amount of carbon-14. And then we have our equation we solved earlier. T equals -1 over k times the natural log of nt over n0. Well, we need K, right? Okay, we need K. So K equals 0.693 divided by T1 half. 5,730 years. Um, 1.209 times 10 to the, oh wait, that's, put the underline in the wrong place. Not that it really matters. Times 10 to the minus 4 per year. So we have minus 1 over 1.209 times 10 to the minus 4 per year, natural log of 0.89. And what's that come out to be?
Oh.
964. So is this thing old? 964 years? Yeah, it's old.
Pretty old.
Does it come from 500 BC?
No.
No. It comes more from, 464 AD. So, could it be authentic? No. If it's off by a few years, sure. If it's off by 5% or less, definitely, because this technique has some error in it. But, off by this much, it would not be accurate. Any questions? Uranium/lead dating. Radiocarbon dating has some limitations. The object has to have been alive at some point, right? So, a clay pot, probably not, because, the clay was in the ground for a really long time, possibly before the pot was made, and it just doesn't work. And the object has to be less than 50,000 years old. So there are some things that are older than that people are interested in. So we can also look at the ratio of uranium-238 to lead-206. Igneous rock, that's rock that comes from volcanoes. It would originally have some uranium-238 in it, which decays to lead-206 with a half-life of 4.5 times 10 to the 9th years. Yeah, it's a long time. The half-life is much longer, and so we can date something that's much older this way. One of the problems is, what if that rock had lead in it when it was formed? Well, the lead that results from the radioactive decay is lead-206. Lead that was naturally occurring in the rock at its formation would be an average of all the different isotopes of lead. And so the composition is different, and so that can be corrected for. So a rock contains a Pb206 to U238 mass ratio of 0.145 to 1. Assuming that the rock did not contain any Pb206 at the time of its formation, determine its age. Well, we're going to need the T1 half, right? Which was given to us on the previous page. So T1 half is 4.5 times 10 to the 9th years. So we could calculate the rate constant, 0.693 divided by that. It's going to be pretty small, huh?
Yeah.
1.54 times 10 to the minus 10 per year. Now, how do we get that ratio of now to original?
Original is 1.
We could say that the original is 1. So N0 is 1. And then what's NT? But the problem with saying 0.145, which would be easy, right? 0.145 is the amount of lead-206. And the 1 is the amount of uranium-238. So what we have to do is we have to figure out how much uranium-238 is left in this sample. Well, these are most likely done by masses, right? So we could take this as the mass of lead and convert it and find out what would be an equivalent mass of uranium. And that's the amount that's left, right? So we're going to take 0.145, and we can choose any unit we want because the units are going to cancel out. Let's use grams. Grams of lead-206. What's the molar mass of lead-206? 206. We're looking at a particular isotope here, right? Now, is it exactly 206? No, but is it really close? Yeah, it is. So grams cancel out. And then we have 1 mole of uranium for every 1 mole of lead. And then we need the mass of uranium-238. 238 grams per 1 mole of uranium-238. So that gives us 0.1675 grams of uranium-238. That's what's left. Because for every 1 uranium nuclei that decayed, we got 1 lead nucleus. Right? So we take this amount of lead and convert it to uranium. This is equal to NT. So now we can plug things in. Where can I fit all this in here? We end up, in these problems, we end up using the same rearrangement of this equation over and over again. 1.54 times 10 to the minus 10 per year. Natural log of 0.1675 to 1. Comes out to be what? I got 1 times 10 to the 9th years.
What do you get?
1 times 10 to the 9th?
No, that. Well, no, those.
Hmm?
No, those.
I got 10 cents to the 10.
Yeah. I think
Let me double check. Okay, so after a bit of discussion here, we have come across the problem. This is not the original mass. The 1 is how much uranium-238 is left. And this that we calculated is the amount of uranium that decayed. So how much was there originally? The sum. The sum of them. So we have to add those together. Oh yeah, 1.1675 grams.
And our index of T is 1.
So let's see here. Give me my eraser. Oops. That's not the eraser anymore. What happened? Okay. See, I was, trying to be really smart and actually write things down. I actually wrote this down and see how much it helped. It helped not at all. That's not the 0, it's the T. Okay, so that's what we actually have left now.
No, or now is 1.
I'm sorry, you're right. Wow. That just is nothing. That's how much decayed.
Yes.
Decayed. Oh. What would I do without you guys? Well, I wouldn't be here teaching is what I would do without you guys. I'd be home knitting. It would be lovely. So this is all your fault. I can spin anything.
Yeah, yeah.
Okay, now, put that through your calculator. That does come out to 1.0 times 10 to the 9th.
Yeah, it does.
I'm like, but that's the answer I have down, and I checked it in the back of the book. It must be right. So the book never makes mistakes. Okay, so that was really a botched example. Any questions?
No,
Like it wasn't confusing enough. I made it more so.
I understand. A little bit.
So you really have to think these things out. You might need to draw some pictures to be clear on what you're using. You can't just take numbers, the 0.145 and the 1, and stick them in there. Okay. The age of the Earth. Yeah, the age of the Earth. So, people develop a technique like this, and then people go out and like, ooh, here's a rock, let's see how old it is. So, all over the globe, people have been measuring the age of rocks using radiometric techniques. And so they find that on every continent, there are rocks that are over 3.5 billion years old. The oldest are about 4 billion years. And it seems reasonable to assume that the Earth is at least as old as its rocks. Right? Now, there are a lot of assumptions in there which could be challenged and investigated and maybe proved or not. So this is very simplistic, but it seems reasonable, assuming the Earth is as old as its rocks. And meteorites occasionally hit the Earth. These are coming from outer space, right? So they get pieces of these and measure or estimate the age. And those are about 4.5 billion years old. Those, we assume, were formed at the same time as our solar system. So based on all of that, the best estimate of the Earth's age is 4.5 billion years. The universe is estimated to be 13.7 billion years. It would be bad if the Earth's age was larger than the universe's age. So that's where scientists stand right now. I'm not going to test you on that. It's just fun facts, yeah. It's interesting. It's an application of science to questions that people have had for a long time. How old is the Earth? There's a really good book, now I've forgotten the guy's name, but it's called A Brief History of Nearly Everything. And it's the history of science, for the most part. But really, really fascinating. Looking back, the 1700s and stuff, and they were trying to figure out how old the Earth was, and some of their calculations were pretty crazy. Also, trying to figure out how big is the Earth? How do you measure that when you don't even have an airplane, right? So really, really interesting peek into the history of science. I recommend it.